Alright, welcome back. Homework 2. We're talking about energy in general. And the different forms of energy and the different forms of energy transfer, specifically work and heat. We also got internal energy, enthalpy, and all that good stuff. Okay. And so we're on problem number 5 now. Okay, so this says, in a refrigerator you have 4 major components. And so this is kind of an allusion to what we're going to see in when we talk about cycles. So we've got, so this is really like, how does your refrigerator actually work? Well, what you have, now it says here, okay, you have food, okay, so, bone, okay, so we got some chicken, okay, or ham. I like to think it's chicken, but that's drawing like ham. Okay, so we got ham that's being let's see, it's cooling off. Okay, so and so cooling off. What does that mean? Okay, now when I cool something, now heat flows only in one direction. Okay, so first off, it's heat, right? I mean, cooling is definitely a heat thing, not a work thing. Okay, so it's definitely a heat thing, but it's cooling. Okay, so when something cools, well, the heat flow is always one direction, from the hot thing to the cold thing. Okay, so it's not so much my meat is getting cooler; it's my meat is heating up my fluid. Okay, so I have my fluid here. Okay, so really, the heat flow is this way. That my meat is heating up my fluid that's flowing in this pipe. Okay? Alright. So cooling the food. Okay, and then it goes into a compressor. Okay, so this is the typical picture for a compressor. Okay. And a compressor is basically like a pump, but more than that. Okay. Okay, it comes out, and then let's see, what does it do next? Condenser where the compressed fluid is cooled off. Okay, no, compressor to bring the cooling fluid back to a liquid. A condenser where the compressed fluid is cooled off. Okay, so I have a condenser here. Okay, where it's cooled off. Okay, so here, so it says cool, so I got heat flowing, but I don't know which direction yet. Okay, so condenser, compressor. Okay, and then I have a throttling valve. Okay, that expands my fluid. So that it's ready to cool off my food once again. Okay, so this is basically a refrigeration cycle. This is, again, allusion to what you'll see in chapter 3. For us, it's going to be at the end of the semester. Okay. So now a compressor is like a pump. Okay. This is, this is the kind of the coils. The condenser is kind of the coils in the back of. Now there are coils that are things, but it's so we got heat transfer here. Okay, so now here, but what does it specifically say? It's saying condenser. A condenser where the compressed fluid is cooled off. Well, if this is cooling off, well then this is cooling off. The heat's being taken away from my system. Okay, basically heat is being released, exasperated. Okay, so here heat's going into the system. Here heat's going out of the system. Okay. Now a compressor. Okay, well, compressors are pumps. Okay, what kind of energy transfers are going on there, if there is any at all? Well, there's rotating shafts. So this has work going into the system. Okay, and it has work going into a system. So, that's why you have to actually plug in your refrigerator. Okay, So the electrical power goes to that compressor. That compressor does work on the fluid to keep it flowing, but also does, to get it to the liquid state and all that other good stuff. Okay, now this valve, well, this is just for sudden expansion. Okay, so you get a sudden drop in pressure. A sudden drop in pressure, which also drastically drops your temperature. So you have a high pressure system from the compressor, you release its heat, and then you drastically, really a valve is just a valve. It's a thing that turns open that, okay, I'm going from a thin pipe to a big pipe. It's really kind of what it is. Okay. But there's no shafts, okay? So there's no shafts. The boundary's pretty much the same, so there's really no boundary work, so no boundary work. The pipes are technically the same, it's just the way, valve works. That's more of a fluids thing on the exact mechanics of a valve, but basically a valve causes some expansion. But I'm going to tell you that it has no boundary work, okay? It has no shaft work. And actually, when we get into energy balances, we're going to find that there's no change in flow work. Okay, so there's actually no work at all on this thing, and it happens so fast that it's actually adiabatic also. When we draw our boundary around that thing. So, for the valve, there's no energy transfer. There's no heat, there's no work, it's just a fluid going through, cooling off by changing its pressure drastically. Okay. And of course, now that it's cool, it can suck the heat out of our meat. Okay. Let's see here, what does it say? I think, from the diagram of this process, draw where things are adiabatic, where heat is flowing from to, and where the work is being done on or by the system. Okay, so there's definitely heat transfer going on here, but there's no work here. It's just happening. Okay, other than flow work, but we're never going to account for flow work. Okay, not explicitly. So no work there, no work there. There's definitely work here, and it's definitely being done on the system. Now, how do I know it's being done on the system? Well, I have to compress it. I have to, so if I'm compressing something, so think about a spring in terms of the concept of compression and expansion. So I have a spring, okay, and the spring compresses, okay. Do I exert energy or does the spring exert energy? If I have a spring, like a bed spring, and I want it to compress, well, I've got to push, meaning I do work on the system. If it's going to expand, well, assuming it's not at equilibrium, then it's already compressed, it's going to do work on me. Okay. All right. But we want to assume that this is insulated. So we'll put the little hashtags here, okay, to indicate it's adiabatic. Why do we want to assume it's adiabatic? Well, we want all of that work going into the fluid, not into any heat. Okay. Now, is that true? No way. That's the worst assumption on the planet. But it's what we have to assume, or what ideally we want to assume. Okay. It is not adiabatic, but we want to assume it's adiabatic because we want none of this work to go to the heat of the surroundings. We want it all to go into the fluid. Okay. Here, there's no work, there's no boundaries again, so this is just heat transfer. And here, again, there's nothing going on. It's just going through an expanding valve. Okay. So there's no work, but it's also adiabatic because it's so fast. Okay. It doesn't stay at the same temperature. It cools off rapidly. Think about those air canisters that you use to clean your computer. Well, what happens? It gets cold, right? Because you have a sudden expansion of this liquid into a gas. So that's kind of what's happening here, yeah, essentially. So heat transfer into the system, heat transfer out of the system, work into the system, adiabatic, and no work. And of course, you got flow work throughout the whole thing, but remember that gets accounted for within enthalpy, but not really as a boundary thing.